All right, welcome everyone. Thank you for joining us for the DeFord Lecture Series. My name's Elizabeth Catlos, and I'm a faculty member in the Department of Geological Sciences at the University of Texas at Austin. We're part of the Jackson School of Geosciences, and the DeFord Lecture Series is our departmental seminar series. It's been a requirement and tradition for all graduate students since the late 1940s. The lecture series is named after Professor Roland DeFord, who joined the university as a professor in 1948 with the purpose of enhancing the graduate program of the department. Our lecture series is supported by a range of endowments, and today's speaker is the Robert H. Kyler Endowed Lecturer. This lecture series was established in 2008 with a gift from the estate of Benjamin Monroe Anderson. Kyler was born in Austin, Texas in 1908, and he was associate professor of geology at UT for 17 years. His untimely death while serving his country on a training mission with the Army Air Corps in 1944 was a staggering blow to not only his friends and family, but to the science of geology and specifically micropaleontology and subsurface geology. Ben Anderson earned a degree in geology from UT Austin in 1939, where he was a member of Sigma Chi fraternity. He also spent a year studying aeronautical engineering at the Curtiss Wright Aeronautical Institute in California. And in 1945, he co-founded the Anderson Greenwood Company to design and build aircraft, which became a world leader in precision valve technology. Ben Anderson died in 2007 at the age of 91. So our speaker today will be introduced formally by Dr. Daryl Tremaine, who's a research program coordinator with the Jackson School's Environmental Science Institute. Dr. Tremaine?
Hi, thanks, Liz. Okay, so I have the pleasure of introducing Dr. Kathleen Johnson as our DeFord lecturer for this afternoon. Jay Banner and I nominated Kathleen not only because of her contributions to understanding of speleothems, paleoclimate science, but also because of her passion and her commitment to elevating the voices of URM students and community stakeholders. Kathleen earned her bachelor's in geological science from the University of Michigan and her doctorate in geology from UC Berkeley. She did her postdoc at Oxford with Gideon Henderson and focused on understanding speleothem trace element and isotope systematics and generating millennial to orbital scale paleoclimate reconstructions for the Asian monsoon. And she co-authored one of my favorite papers entitled A Test of Climate, Sun, and Culture Relationships from an 1810-year Chinese cave record that neatly delineated the rise and fall of Chinese dynasties as a function of hydrology. Kathleen is currently an associate professor in the Department of Earth System Science at UC Irvine and serves as her department's first vice chair for equity, diversion, and inclusion. She champions JEDI efforts on many fronts, including at the promotion and tenure undergrad and grad levels at UCI, as well as serving as a mentor in the AGU Bridge program, as an Unlearning Racism and Geosciences participant, and as a member and liaison to the Native American community. Kathleen's been bestowed a number of honors, including the Gary Comer Abrupt Climate Change Fellowship, Outstanding Contributions to Undergraduate Education, the Chancellor's Award for Excellence in Fostering Undergraduate Research, the Bromley Award for Minorities, and being named a Fellow of the Geological Society of America. So her talk today is illustrative of a shift in scientific communication that I'm very happy to see. And she'll be offering some paleoclimate perspectives of the Southeast Asian monsoon sprinkled with justice, equity, diversity, and inclusion. And with that, I'll say, welcome, Kathleen. The floor is yours.
Thank you so much for that really nice introduction, Daryl. And thank you, Jay and Daryl, for the invitation, and Liz for all of the coordinating. I'm really excited to give this talk today, though, as I'm sure you're used to hearing, I would much rather be giving this in person to you all in Austin, which is a wonderful place where I was able to visit a few years back when I co-organized a workshop on speleothems at the Jackson School together with Jay. So let me go ahead and share my screen here, and we'll go ahead and get started. So the title of my talk today is Monsoons and Climate Change, a paleoclimate perspective from Southeast Asia, but I'm also going to spend some time at the end talking about some of the outreach and JEDI work that I've been doing with Native communities for many years now. So I will try and hopefully not rush through everything too quickly. Before I start talking about the research that we're doing in Southeast Asia, I of course want to acknowledge the many collaborators and students that have contributed to this work. Anytime you're working in international field locations on very multidisciplinary projects, we rely on the expertise of a lot of our colleagues from fields including paleoclimate, climate science, geochemistry, as well as archaeology. As you'll see later, we've worked closely with several archaeologists in Southeast Asia. And we also rely on really strong relationships with our local community members in the places where we're working. And today I'll be mostly talking about our results from Laos. So several of our Lao colleagues as well would not have made this work possible, as well as funding from NSF, of course. All right, so I know that some of you might be very familiar with speleothem-based paleoclimate records, given the expertise of Jay Banner and Dan Breeker and others at the Jackson School. But for those of you who might not be, I'm going to include some basics. So first of all, in terms of thinking about the reasons for studying past climate change, there are many motivating factors, all of which have to do with helping humans better predict and prepare for future climate change. So by looking at natural climate variability over longer timescales than what we're able to do with instrumental climate data, that allows us to separate out natural variability better from the human forced component of the climate changes that are occurring. It helps us by comparing with other records and forcing climate forcings. We can try and look at the different impact of external factors such as changes in solar insolation versus internal feedbacks and internal climate processes such as things related to coupled ocean atmosphere variability, for example, through ENSO. Paleoclimate data also helps us set boundaries and alternate conditions for climate models that simulate reality. So we can use the paleoclimate data to as a target for paleoclimate models, and there's more and more sophisticated ways that models and data are being integrated together to do that and ultimately lead to hopefully improvements in the dynamics that are characterized in climate models and therefore in the future climate projections. So this map here is showing a map of the global monsoon regions of the world, which are regions that are characterized by strongly seasonal precipitation, usually associated with a seasonal reversal of winds, surface winds, due to the different heating of the lands versus the ocean. And much of my research over the years has focused in Asia, and I've worked a lot in China, and today I'm going to be talking about some records from there, but as well as from Southeast Asia, where we've been working for several years. And the reason why we're interested particularly in the Asian monsoon is partly that climate models still struggle to agree on even the sign of precipitation change in the monsoon region, let alone the magnitude of that change. And that's partly because the monsoon is an incredibly complex part of the global climate system that interacts with virtually every other part of the climate. Climate models and physics tell us that as global warming occurs, the monsoon circulation is actually expected to weaken along with the Hadley circulation, and potentially, but the impacts on rainfall are likely to, most models suggest that large-scale monsoon precipitation will increase due to thermodynamic effects. So warmer atmosphere can hold more water, basically. However, the exact regional precipitation patterns that are likely to result are unclear. The Asian monsoon is actually a very large system that consists of several sub-monsoon systems, such as the South Asian or Indian monsoon, the Southeast Asian monsoon, the East Asian monsoon, and many other different ways of subdividing it. And so if you look at this map on the right here, what this is showing is that there's the lack of stippling is basically telling us that there's very little agreement about the sign of regional precipitation changes across much of the Asian monsoon region here. And so this is a challenge that paleoclimate data can help address by providing more and more detailed pictures of how climate varied naturally in response to different factors. Okay, so further motivation is the impact that even small variations in the monsoon have on people living in Southeast Asia. So Southeast Asia is very dependent on monsoon moisture for industry, for agriculture, for transportation, and for basic human needs. And yet in recent years, we've seen more and more impacts of climate extremes. And at the same time, there's this very complex socio-political situation there where hydropower and dams are being built at a very rapid rate, as one of which you can see here, which wasn't there the first time we went to our field site in 2010, or was under construction, and now is one of the larger dams within the Mekong Basin. And here you can see some impacts, some pictures showing recent droughts in the Mekong Basin, which obviously had some impacts on people in these areas. Similarly, there's been some really severe floods that have happened in recent years. You may remember in 2018, there was a dam collapse actually due to an extended period of heavy rain in southern Laos. And the result of that was the flooding of displacement of several villages, and many people were killed during that event. And the floods actually went all the way downstream into Cambodia. And on the right here is a picture that actually is from recent flooding in Vietnam this past fall in 2020, where over 90,000 people were displaced, hundreds of people were killed. And this is actually very close to one of our other field sites that I won't be talking about today, where we've more recently been working in central Vietnam. And so hydrologic extremes and how they might change is something that's extremely relevant to people in this area. And so just to bring that a little bit closer to home, this is actually a picture of a bridge really close to one of our field sites, downstream from one of the caves by just a few miles. And you can see that this bridge was destroyed by some severe flooding that happened. And you can see some twigs and stuff up here, flood debris. And just as an example of the resilience of the people there, this is the answer to that bridge being collapsed, and they've built this really efficient, incredibly efficient car ferry system that we have to go across in our truck to get to our field site, and it's powered with some little car motor that's got a rudder attached. So that's always an exciting highlight for new students whenever we take them to Laos for the first time. Okay, so moving on to some of the science that we're doing then to try and understand natural climate variability in this region. For those that are new to speleothems, if there's any of you, they are cave carbonate deposits, primarily calcite, but can also be formed from aragonite, that are precipitated in caves as a result of infiltrating water. So acidic water makes its way down through the bedrock, dissolving limestone bedrock. And then when that water enters the cave, it degasses, precipitating layers of calcium carbonate, which can be continuously precipitated over many thousands of years. And one of the main advantages of these deposits is that they can be precisely dated with uranium thorium dating, which allows us to construct an age model for a layered laminated deposit like the one you see here on the left. Also critical is the fact that the chemistry of that calcium carbonate is reflective of a number of climatically sensitive processes. So we can look at things like oxygen isotopes, which is primarily controlled by the composition of rainfall that falls above the cave, as well as the cave temperature. We can look at carbon, which is affected by soil and bedrock processes. I'll say a little bit more about those in a minute, as well as trace elements. And then there's more and more new emerging proxies in speleothems that can give us more and more information. And that's important usually to use a multi-proxy approach, because as with any proxy method, there's always going to be some uncertainty. And so when we can show that the inferred hydrologic changes that are recorded in our sample are recorded by several different parameters, then that gives us greater confidence in those records. Okay, so the study area that I'm going to be talking about today is a single cave called Tamdun Mai Cave. You can see a map of it down here. It's actually one of the longest caves in Laos. The entrance is up here, and you can see most of our samples that I'll be talking about today came from this area way back here along a ledge that drops down to this lower river level, which actually continues on for a couple of kilometers. So it's a relatively easy cave to access, thankfully, and just requires a few short drops on a rope, but it's always fun to go there anyway. And it's actually, to get to this cave, we have to drive a few hours, take a boat up the river for a couple hours, stay at a village, and then travel by boat to the cave every day. It's located along the Namu River, and we've been studying this cave since 2010. And have been trying to monitor it as thoroughly as we can, though of course, compared to the monitoring work that's been done in Texas caves, which are much easier to access for you all, we are only able to get data, some data like temperature, humidity, CO2, drip rate, we can measure for some longer periods, but much of these measurements, including a lot of chamber measurements of soil processes, soil CO2, radiocarbon, have only been done, once every year or two since this time. Our cave is located up here in northern Laos. It is strongly dominated by the summer monsoon, so the majority of rainfall happens in the summer. And here's some pictures of just some of the monitoring work we've been doing, collecting drip water, collecting rain and measuring rainfall, and monitoring calcite in that cave. And the purpose of that is to better understand the controls on the proxies in that particular site. Okay, so just to say a little bit more about some of the proxies, oxygen isotopes is the most common proxy used in speleothems. And it's, as I said, it's dominated by the variation in the precipitation delta 018. But interpreting that in terms of climate has proven to be a long-running controversy, as there are many complex processes that can impact the precipitation isotope signal. So some of those are listed here, and I'm just going to read through them. I don't want to spend too much time on this, but they're the amount of rainfall, the seasonality of the rainfall, because there's a strong seasonal cycle. If you shift the seasonal balance, you can shift the mean, which is what actually drips into the cave. Westerly jet transitions is a new hypothesis that John Cheng proposed, which basically impacts the moisture source region that's providing the monsoon rainfall. Upstream rainout is something that is the dominant factor that I think at our site, which is basically the fact that the 018 signal represents a integrated signal of all of the fractionation processes that happen between the moisture source region, being the tropical Indian Ocean in this case, and the cave site. So the more rainfall you have upstream, the more convection you have over the ocean and Indian monsoon region that lie upstream, the more of the heavy oxygen 18 bearing water gets rained out, and therefore the signal at our site gets lower. So it really should be considered as more of a regional signal. And so you can see this record at the top is the Chinese speleothem record from Cheng et al. In 2016, which is a compilation for many different stalagmites that is incredible and goes back over 600,000 years. And in pink is the Northern Hemisphere summer insolation record. And you can see that there's this extremely tight correspondence between those two. And this has been used deservedly so as really strong evidence that the strength of the Asian monsoon is dominantly controlled by insolation on these timescales. And so one question we have, though, and this has been quite a big debate that I don't have time to go in great depth into, is this delta 18 signal really telling us about rainfall across the monsoon region, or is it does rainfall in these different regions actually follow this insolation trend? And so to answer that, we can look at some other proxies other than oxygen isotopes. And so I guess I'll stop there for now and go on to the next slide. But basically, that's sort of one of the questions we're trying to address is how does the monsoon rainfall pattern vary in comparison with that insolation signal? And the reason why we suspect one of the reasons why we don't expect that rainfall across that entire monsoon region is going to all vary in phase with insolation is that that's not what we see in the recent instrumental data. So here's a image showing EOF analyses of summer rainfall across the monsoon region. And you can see these red and blue areas are basically areas where rainfall is anti-correlated on these interannual timescales at least. And we also have found evidence in paleoclimate data that these types of spatial patterns persist on longer timescales, for example, potentially during millennial scale events. And so one of the ways we can address this and really start to look more at how these forcings might impact regional precipitation change is by filling in gaps in the paleoclimate record and getting more robust records. And so that's both, we're trying to do both of those in Southeast Asia in our work, because it's actually a region where there's very few data points that extend beyond the tree ring record, which is relatively good in that region. There's some newer lake records, which are quite good, but we published and developed some of the first speleothem records, which is what I'll show you today. Oh, just to add one more point to that, sorry. This on the right is showing 3 different speleothem records from regions that are quite far afield, from Central Asia, from the East Asian monsoon region, and from India. And you can see that there's really strong similarities between these 018 records from these very regionally distant areas. And so that also supports the signal is really a large scale signal of monsoon intensity that we think is dominated by upstream rainout, and previous modeling studies have supported that as well. Whereas other proxies might be able to tell us something more about the different, the nuanced rainfall patterns. We've done quite a bit of analysis of modern precipitation data using existing data, as well as isotope-enabled model data that has been nudged with reanalysis data, in particular a model called IsoGSM. So here's an analysis where we compared these simulated 018, and the reason we had to use simulated 018 is just the data sets that exist there are quite short, whereas we can use this IsoGSM model, which has already been validated for large regions of the globe, to look at dynamics controlling that signal. And so we find on interannual timescales, if we correlate the 018 from the model with sea surface temperatures here, you see this very strong ENSO-like signal, indicating that ENSO is a very important factor controlling at least interannual variability in this region. We also find these strong correlations with sea level pressure over the Indian Ocean. And this is work that was done by my former student, Hong-Ying Yang, I should say. And this low sea level pressure over the upstream areas is linked with increased convection, increased rainout, leading to more negative 018 at our sites. And then similarly, vertical wind shear, or the strength of the Walker circulation, which is tied to the monsoon intensity, is also an important factor, which you can see in this bottom panel. And so, like I said, just to summarize, the 018 should be interpreted as a large scale proxy for monsoon intensity and maybe upstream rainout over the Indian Ocean and the tropical, the Indian Ocean and the Indian monsoon region, but not necessarily reflecting rainfall at our study site. And so to do that, we want to look at other proxies, one of which is carbon isotopes. We've done a lot of work with both C13 and radiocarbon. And speleothem delta C13 controls are also complex, but the nice thing about them is that the majority of them are dominated by local processes. So if we can study those controls, which include vegetation, both type and sort of intensity, bedrock dissolution, CO2 degassing related processes, as well as prior calcite precipitation, which is calcite that's precipitated above the cave, basically. And similarly, radiocarbon is a newer method that we've worked on, where we believe that dead carbon proportion, which is basically the fraction of carbon that's coming from the bedrock. Because if you look over here, the sources of carbon in the speleothem are the soil CO2, the bedrock, And those are the two main sources. A small amount of atmosphere may get in there if you have very low soil productivity. So the amount of carbon that's coming from the bedrock can be determined by measuring radiocarbon, because the limestone is free of radiocarbon because of its age. And the soil represents a relatively modern, depends on the age of soil organic matter, but it's relatively modern. And so if we use radiocarbon dating in combination with a uranium thorium age model, we can calculate how much carbon is coming from the limestone, and we call that the DCP. And we believe that that is dominantly driven by the carbonate dissolution regime, and where the degree of open versus closed system dissolution, meaning is dissolution of the bedrock happening in the presence of an unlimited pool of CO2, or is dissolution happening removed from with a smaller limited pool of CO2? Because if it's in the presence of CO2, you can have constant exchange between the DIC pool and the CO2 pool, and therefore you might get a really modern, very small bedrock contribution. And we anticipate that that occurs when it's drier. So you have these more open system dissolutions when you have a greater proportion of air pockets, basically, in the region above your cave. And then on the other end of the spectrum, if you had a really saturated epikarst region, you have less opportunities for that open system type dissolution, and you can get theoretically up to 50% dead carbon fraction. And so we've been studying this through a number of sort of modern monitoring studies, as well as speleothem studies. And we through comparison with other proxies, we think that the DCP in many cases can be a valid proxy for hydroclimate or for local water balance as well. Okay, so and then the third category of proxies that we're using, and I'll talk about today, are trace elements. So I already mentioned prior calcite precipitation, which is this idea. This is a very simple cartoon version that one of my students made. And this is showing water infiltrating through a fracture in this case. And as it's going, it has the opportunity for CO2 degassing to occur, which leads to calcite precipitation. And because of the partitioning of certain trace metals into calcium carbonate, the things like magnesium and strontium have a very low partition coefficient, much less than 1. So they prefer to stay in the liquid phase. Whereas the calcite that's precipitated basically leads to enrichment of magnesium and strontium relative to calcium in the remaining drip water. So the more of that occurs, and we assume that the more of that occurs when it's drier, you get increased magnesium, strontium, calcium, which ultimately can be preserved in a stalagmite. In the same way, carbon isotopes are also affected by this process, where carbon-12 preferentially degasses during degassing, and then the remaining water is enriched in C13 as it infiltrates down through the epikarst. So we can also look for the relationship between things like magnesium and strontium and carbon isotopes as a test for the presence of this PCP process. Okay, so hopefully some of that will become more clear as I show you real data. So I'm going to go through 2 case studies of different speleothem records we've developed using these proxies. The first is a 38,000-year record. So we can look at climate variability over orbital and millennial timescales in this region. This is the 2 speleothems on the left here, along with their age models. So this top one, TM21, you can see how these blue dots represent uranium thorium ages. The error bars are smaller than the size of the symbol. But you can see that this one has several periods where it actually stopped growing. So these growth hiatuses, so it's not the perfect sample. However, it does serve a very useful role to replicate our beautiful record, which is from the TM17 stalagmite, which is a 60 centimeter long columnar stalagmite dated with 25 uranium thorium dates. You can see the really tight age model here. And on the right are the carbon and oxygen isotope data from both. The grays are the TM21 data, which replicate quite well our TM17 record over here. And so first, if you look at the oxygen record, you can see, if you are used to looking at such records, you might recognize that it looks very similar to records that you might find from China. The Chinese speleothem record I showed earlier has this very similar pattern where we have enriched delta-18, some more positive delta-18 shifts during Heinrich events, which are these abrupt cold events when the AMOC, or the Atlantic Meridional Overturning Circulation, weakened or shut down even, and caused widespread cooling of the Northern Hemisphere. And that cooling also manifested as a southward shift of the ITCZ and a weakening of the Northern Hemisphere monsoon systems. And so we see that for each of these events, as well as for the Younger Dryas, and for a similar event that happened during the Holocene, the 8.2 kiloyear event, this little blip right here. Interestingly, though, what we noticed with this data is that if we look at the carbon, we see some similarities and also some interesting differences. So here we have strong shifts towards positive C13. And if you remember, that shift towards positive C13, we interpret as drier conditions, either due to some combination of decreased soil productivity, shift towards perhaps more C4 vegetation, or perhaps more prior calcite precipitation. All of these mechanisms together all would lead to the same direction of change. And so the Heinrich events and millennial scale events seem to actually show that, okay, even so when these 018 enrichments occur, it appears that it also got drier at our study site. So that is great, because it shows that the 018 signal is also potentially somewhat sensitive to local rainfall, or that these large scale upstream changes extended into mainland Southeast Asia. But if we look at the orbital signal, and it's a little challenging because we don't yet have longer records to look at multiple orbital cycles, but the Holocene is a great place to look to see that orbital trend where you have this early Holocene minimum in delta-18. And I should note, when I say minimum, all of these y-axes are flipped, as is the convention in our field. And so this minimum, which would indicate the strongest monsoon period in the early Holocene, during when the insolation was at its maximum in the summer, that's consistent with this orbital monsoon theory. However, if we look at the carbon isotopes, it shows something quite different. It shows that there is actually an enriched period of enriched values in the early Holocene, coincident with the insolation maximum. So that suggested to us that maybe there is some sort of decoupling between the large-scale monsoon intensity and the regional precipitation in mainland Southeast Asia. At this site, we actually see the wettest conditions are more towards around 5,000 to 7,000 years ago, which is different from the timing that we would infer for the monsoon maximum based on the 018. So that's sort of one of the things we're going to look at with by comparison with some other records and proxies. Okay, so there's a lot going on this slide, so I won't spend too long going through it. I'll just point out some of the key features. So this is a comparison of our delta-18 record in blue down here at the bottom, along with several other oxygen isotope records only from across the monsoon region. So we have records from India in yellow, China in red and purple, and then we have the Greenland ice core record. And this record in purple down here is a bivalve record from a lake in Thailand, which is the only other oxygen isotope record spanning this time period from mainland Southeast Asia. And what you can clearly see, especially if you could just compare with the China composite record, is that they're extremely similar. And we're certainly digging into some of the smaller, more fine differences between these, which are certainly going to be useful to look at to gain more insight into some of the nuanced differences between these records. But in general, the fact that these are so similar supports the idea that this is really a large scale proxy for the monsoon. The orbital scale variability is in phase with the Northern Hemisphere summer insolation. The millennial scale variability, which is linked to AMOC, is seen throughout all of these records. And we even see some evidence for some influence of Dansgaard-Oeschger oscillations, which are these warm peaks here, although they're not as clear as they are in the Chinese record yet. But in general, we interpret this as evidence that the 18 record reflects large-scale monsoon intensity driven by upstream rainout, most likely over the dominant moisture source region for the monsoons. And therefore, while this is very useful information, we think that we can gain more information by throwing in some additional measurements. And so some of this work that I'm going to show in this slide was done by my student Chris Wood, who's now a postdoc in New Zealand at University of Waikato, with one of the many cats that we make friends with when we're in the field. And this is our breakfast spot before we head up the river to our cave every day. This is, Chris looked at radiocarbon and trace elements in that same sample in order to gain a better understanding of some of the local hydroclimate changes. And we're still kind of working out some of the details of this, but in general, the dead carbon, the DCP, which reflects contributions of aged soil organic matter and the closed versus open dissolution, is in purple. The trace elements, this is actually the PC1 for magnesium and strontium, which are very similar to each other and very strongly correlated with one another, supporting a prior calcite precipitation interpretation, which we also have monitoring data to support that as well, but I don't have time to talk about that today. Reflectance is another one that we don't fully understand yet. This is actually just grayscale measurements conducted on the speleothem, which is linked to the crystal fabric and whether basically how porous or compact the calcite is. And we find some interesting shifts towards more compact calcite during these drier periods, which we think is further evidence that the Heinrich events were dry, at least. We're not quite sure yet what's happening in the Holocene, so stay tuned for that. The carbon isotope data, as I said, is some combination of PCP, bedrock dissolution, and or soil vegetation changes. And then we have the oxygen isotope data at the bottom. So the trace element data is still somewhat confusing because we actually find shorter excursions towards the beginning of most of the Heinrich events, but not necessarily sustained. And so adding more proxies and measurements can sometimes clarify things, but not always. So, but we do have good evidence based on the radiocarbon signals that we're seeing that the Heinrich stadial 1, especially, we saw no big shift in we see a big shift in dead carbon proportion during the Heinrich event, but it can't explain the shift that we observe in the C13. So we're able to rule out some processes by combining those. For example, the fact that if we increase the proportion of dead carbon, we would expect to see a signal that's quite different from what we see in the Heinrich event C13. And that tells us that probably there were big vegetation changes instead, which explained the carbon isotope signals. So that's something I'm happy to answer questions about, but I'm going to move on to a comparison of the C13 data with some other records to see if we can find further evidence of these dry conditions, especially during the early Holocene insolation maximum, which is the main area where this is the timing of this Holocene rainfall maximum across Asia is a long-standing debate. Where speleothem records have disagreed with records that have been derived from marine sediments, from lakes, from loess deposits, and several others. And so this is an ongoing issue. And actually our speleothem carbon data tends to support the idea for this, first of all, for an asynchronous maximum in rainfall across the region, but also for a later maximum in mainland Southeast Asia. And if we compare that with a few of the records that are available, this is a barium calcium record from the sediment core here in the Andaman Sea, which is a proxy for runoff linked to the Irrawaddy River Basin, which drains a portion of mainland Southeast Asia. And the timing of the peak in runoff from the Irrawaddy is consistent with the timing of our wettest conditions in our speleothem record from Laos. So that supports that a little bit. And then similarly, if we go back to this tripole pattern that we see in modern rainfall and that we think might exist on longer timescales as well, we would expect perhaps that our record would share some similarities with records from northern China. And if we look at several of the records, and these are compilations of paleosalt of dune field data, paleosalts and dune fields in northern China, as well as a lake record, a quantitative precipitation record from Chen et al. From northern China, we again see a really similar timing to this maximum. So our hypothesis then is that local rainfall in mainland Southeast Asia is decoupled from insolation or the large-scale monsoon strength, that it may share more in common with records from northern China and potentially India, but less so perhaps with some of the main speleothem records from central China. And so that's something we're working on still, confirming. We've collaborated with some climate modelers. These are results from the GISS Model E isotope-enabled model simulation for 9,000 years ago, which is one of the few models that we had access to from that time period. And this is a collaboration with Allegro Legrand and Tripti Bhattacharya and Jess Tierney have helped with some of these analyses and interpretations. And basically, when you have an insolation maximum in the summer, the effect dynamically is that heats the land surface and moves the maximum of moist entropy or moist static energy along with precipitation north. And it shifts it primarily from ocean to land. And this is also consistent with earlier work that David Battisti and others have done in the last 10 years or so to look at mechanisms from orbital scale monsoon variability. So this shift of moist energy from ocean to land tends to lead to big increases in rainfall in central China and northern India. But you can see that these dry regions around the surrounding ocean, some of which extend into mainland Southeast Asia. And actually you see this, interestingly, for 6Ka as well in many of the PMIPs of the paleoclimate model intercomparison project simulations, showing that mainland Southeast Asia might actually get drier when the monsoon circulation is stronger. So the overall hypothesis is that anomalous subsidence and dry conditions in these peripheral regions lead to explain this different behavior at our study site. At the same time, and this has also been pointed out by earlier work by Posada and others, that at the same time you have some regions of drying, even in those regions that dry, you still see this negative isotope anomaly. And that's driven by these upstream processes. And so this is a comparison of data from the CSIL database with the model, which does a reasonably good job of capturing that. Okay, so let's see, let me check my time. I'm worried, oh dear, yes. All right, so I'll just show a quick couple of highlights from the second so I can make sure I have some time to talk about the DEI work. Okay, so second case study is from that same cave using 3 different stalagmites. And this is one where we really partnered very closely with our archaeologist colleagues. This is Joyce White and Bun Hung, who are the 2 co-leads of this project, the Middle Mekong Archaeology Project, which is actually how we first were able to go to Laos as part of this project. It's a huge, really amazing international project funded by the Luce Foundation and the Penn Museum and others. And and it's a very dominantly, the participants in this project are dominantly from Laos and surrounding countries. And it's a really great project that involves people from archaeology as well as many other scientific disciplines, all aimed at better understanding past environmental change in mainland Southeast Asia, as well as understanding the movement of metallurgy and agriculture around into Southeast Asia, which is a very understudied region, not only for paleoclimate, but also for archaeology. So here we are with some of our team on our way to one of the caves. But in any case, this is work was recently published last year in this Nature Communications paper by Michael Griffiths and I and several other co-authors, and was started 10 years ago. And actually Natasha was also part of that. She worked on one of Natasha Second, who some of you might know, who's probably in the audience, worked on one of these stalagmites here for her undergraduate research project with me here at UCI. All right, so it was a lot of work to put together these records, and we developed these three stalagmite records that are overlapping with each other were combined, which you can see in the black line here. And we have the oxygen isotope data, carbon isotope data, dead carbon proportion in brown, and magnesium calcium in red. And this is looking at these stalagmites were faster growing than the other record I talked to, so potentially more sensitive to these more centennial scale shifts. And we find this very abrupt shift towards dry conditions in all of these proxies. And our archaeology colleagues were extremely excited by this, because it turns out that this time period from around 3,500 to 5,000 years ago, I should know immediately after the wettest part of the Holocene. So it was also a time of really rapid change. This time period is what's known as the Missing Millennia, or was coined as the Missing Millennia, being a period when evidence for human occupation is missing from large chunks of interior mainland Southeast Asia. And it also coincides with a very big shift between a hunter-gatherer culture and more agrarian societies, settled societies that were cultivating cereals. And so the question was whether this shift potentially impacted, this environmental shift was potentially one of the driving factors for that change in societal activities. And we don't yet know the answer to that, but we're working on that as well. But what we do know is that there was this major extended period of dry conditions at our study sites. And we compiled records from across the Asian monsoon region. Again, this is showing that tripole type pattern in modern precipitation. And this is actually especially prevalent during El Nino events or in the summers following El Nino events. And we find that this pattern of precipitation anomaly observed in different records at that time is consistent with what we might expect with an ENSO type mechanism or something linked to the water circulation. And so we worked with Francesco Posada, who had recently published a paper on how the end of the Green Sahara, he published a paper on the Green Sahara and its influence on the water circulation in ENSO during the mid-Holocene, when ENSO variability was suppressed. And so one of our questions was kind of the opposite, which is whether when the Green Sahara, the time period when the Sahara was quite wet due to high summer insolation and various feedbacks, our question was, when the Green Sahara ended then, did that lead to this enhancement of ENSO that we know happened around 4,000 or 5,000 years ago? And so Francesco designed some climate model simulations to look at that. And partly that was motivated by just the fact that the timing of our record shift, which is shown here in gray, is extremely similar to all of these records from recording dust and rainfall over the African monsoon region. And the answer was yes, basically. the proposed mechanism from this paper is that reduced vegetation and increased dust linked to the end of the Green Sahara led to cooling over the Indian Ocean, which you can see down here, shifting of the Walker circulation eastward, which led to widespread drying across Eurasia, which you can see up here. These are precipitation changes along with the location of different records that recorded it, along with our site here. So this potentially links the demise of the Green Sahara through teleconnections impacted hydroclimate over Southeast Asia, which may have impacted cultural changes. And so just the summary of that, I think I just said, so I will just leave that up there for a second. And go on to, again, acknowledge all of my colleagues who have contributed to this work, my amazing students, some of whom you can see here, Jessica Wang, Chris Wood, both recently finished in the last year, as well as our Lao colleagues, Norsang and Sang Pong, Joyce and Bun Hung, Terry, who's our American Texan living in Laos, who is the Lao cave expert who helps us a lot through all of our field work. Michael Griffiths, who was a postdoc with me originally, and we've continued working on this for the last 10 years. And then you can see this nice clean picture of us in the before fieldwork picture, and this is typically what we look like afterwards on the bottom right. And then just a bonus spider picture, because I have many of them and I'm grateful to them as well for not ever attacking me. Okay, so I see that there's questions in the chat, but I guess I'll hold off until, let me talk for 5 minutes or so. I know we have until 10 past for questions. So just a few quick things about the work. As you all know, and I've seen the lineup of speakers in this seminar series, which has been really impressive, and you've had so many great experts on this topic here. So I'm sure you're aware that geoscience has a major diversity issue. This is a nice infographic summarizing some of the data from Bernard and Cooperdock, 2019, where between 1973 and 26, only 20 geoscience PhDs were awarded to Native American women. And so I'm one of those women. It's kind of weird when you can see yourself in such a small number of people. And the fact is that I know probably at least half of the people who are in that group right there, if not more. And so that's a problem because, obviously the Native American communities and Indigenous communities have a number of pressing environmental needs and related to mining and resource extraction, related to climate change, that related to water, that really require expert environmental scientists, earth scientists, and so on. And often it can be really challenging for outsiders or non-Native people to work effectively with Native communities. There's many complex reasons for that, which I won't get into, but in any case, I definitely have made a bit of a mission to increase participation of Native Americans in geosciences. And one of the best ways we can do that is through supporting young people and students. And I do that through a number of different ways, one of which is Lighting the Pathway, which is a NSF funded program, mentoring program. This is Lighting the Pathway to Faculty Careers for Natives in STEM. So in this program, I mentor Native graduate students and postdocs, and some of them are now in faculty positions, and I'm continuing to mentor them through that program. And then I also have worked a lot with high school students, Native high school students, through a number of small one-off outreach opportunities, but also through a formal program which I ran at UCI for 6 years called ASIS, the American Indian Summer Institute in Earth System Science, which was also funded by NSF. Some of my motivation and some of I wanted to share this quote about Native peoples and show this picture. This is actually a picture of my hometown in northern Michigan. It's taken from a hilltop in town. This is a lake that connects to Lake Michigan that my town right here is on. And so I grew up with this, as many Native people grew up with an extremely, close relationship with nature and love of the outdoors. And I think that's a really common thread for Native students. However, there's a lot of this quote by Kyle White, who's a professor at Michigan State. I'm just going to read it because I find it quite enlightening, I think, for those who aren't used to working with Native communities or haven't thought about this too much. But the conservation movement has been as damaging to Indigenous peoples as extractive industries, national parks, ecological restoration projects, conservation zones, and even the use of certain terms, especially wilderness, are associated with forced displacement of entire communities, erasure of Indigenous histories in education and public memory, economic marginalization, and violations of cultural and political rights. So that's a lot, and it's pretty heavy, and it is one reason why academia and environmental science careers have not always been a safe space or a welcoming space for Natives. And so having these types of outreach programs that have really strong engagement from Native students and faculty is one thing that's extremely important. And it's also extremely important to help provide peer support to these students. So this program, we had 131 students from 19 states, representing over 45 tribes. This was just one of the years. We're off in the desert somewhere. And the program was guided by previous work on place-based learning for Native students. We deliberately included tribal members, inclusion of Indigenous knowledge. We actually partnered with the La Jolla Band of Luiseña Indians, which is in San Diego County. And we camped on their reservation for a week and did all sorts of great field projects, cultural activities, brought in lots of elders, community members. They worked with the tribal environmental staff, which included some technicians who were members of the tribe. And so we brought together all sorts of people for this 2-week program, the first week of which was spent at the tribe, and then the second week was spent on campus at UCI doing more college prep work as well as projects. So the scientific themes that it was a Earth System Science program. So it was a very broad curriculum where we talked about Earth as a system, interconnected nature of air, water, land, and life, climate change and energy, which are 2 very pressing issues for tribal people, as well as air and water pollution and waste management are big issues and big environmental issues on tribal lands. So here we are in some of our outdoor lab spaces and classrooms. And here we are working with some of the environmental office staff doing benthic macroinvertebrate surveys or water chemistry measurements, I think. And then back at UCI, we worked on projects, and this is where students really had the freedom to work in teams and work with their communities to develop projects that were specifically driven by their desire to study problems that their tribes were facing. So a lot of the projects often focused on alternative energy, on fracking, on water quality, pollution. Waste management was something I didn't quite realize before running this program, how big of a problem this is on some of the big reservations. There's real challenges there. And then we also incorporated a lot of cultural activities. Here we are at a Chumash village site. We did lots of arts and crafts and storytelling. And I think that's especially important for engaging Native students. One of the things you often hear as a Native in STEM is that people feel like you have to separate that Native part of yourself from your scientist part of yourself. But if we want to make geosciences more inclusive and welcoming for Native students, we need to invite the whole student to bring their whole selves. And that includes things like, understanding that they need to, they may have responsibilities to their family and their communities. They may need to go home for ceremonies. They may want to incorporate Indigenous knowledge in their research. And that is science. Indigenous science is science. And so I think that just helping build these students' sense of Native identity was an incredibly important part of this. And that's was shown to be one of the most significant outcomes based on our evaluations that we did of the program. And then one of the most important things too is just bringing these people together, building the peer network, because each of these students, many of them were, you know, the one really smart kid that they knew, or the one kid who, you know, was interested in science, or the ones or took school seriously, or who wanted to go to college. So having them, all of these like-minded students brought together was like incredibly powerful. And one of the best things that got created, because I know that these students are, many of them are still really good friends. They talk to each other. They're in Facebook groups on TikTok or whatever. I don't know if they have a TikTok yet. That didn't exist at the time, but they might. Anyway, they have continued to support each other, and we continue to support them throughout. So it really was like a family. And they're incredibly motivated to protect the environment and help their communities, and in order to help them achieve their goals, I think that having that peer support is key. I realize it's already 3 o'clock, so I apologize for talking so long, but I also just wanted to throw this up here, which is a laundry list of some of the other things that we're doing. So our department, I helped write this statement together with a couple of graduate students. That is our departmental commitment to ending anti-Black racism in STEM and in academia, that was signed by 100% of our faculty members. And it has several activities that we are accountable for. So it's more than just a performative support statement for Black Lives Matter, but actually hopefully is leading to real change. So anyone can log onto our website. This was the banner on our website all summer, and I think you might have to flip through and find it on there now, but it's available. And then we're also, as was mentioned, we're one of the first partner departments for the AGU Bridge program. So we'll be doing the 2nd year of admissions through that program this year. We have several other anti-racism initiatives, both grassroots and also top-down ones, as I'm sure UT does as well. And there's a series of workshops that I've been involved in organizing. You may have had some of the other organizers here, the Cultivating Leadership for Change and Justice in the Geosciences, which have been really fantastic. We held a workshop at GSA. At the NABG conference, there was sort of a introduction to the workshop series. Then at GSA, we had our first workshop. We had one at AGU on challenges to diversifying faculty in the geosciences. And that one, if you go to the Ethics and Equity Center for AGU, there's a recording of that workshop on the website. And we did another one that was led by students about student work on DEI issues, and that was held at the AMS conference recently. And then we'll be having another one in March that's kind of checking in and looking back at what progress has been made. So I would recommend looking those up. And yeah, I think I'll stop there.
All right, well, thank you so much, Kathleen. That was absolutely riveting. All of the records that you showed are really captivating, and I love the fact that you're stacking so many of them on top of each other. And thank you for all this excellent information about JEDI activities. I think it's really important that we all take stock in this movement and go in the same direction.
I want to thank everyone for coming, and thank you, Dr. Johnson, for a great talk. Very interesting from a bunch of different perspectives. And yeah, I think I can end the DeFord, and I hope to see everyone next Thursday.
Well, thank you so much. And feel free to email me, anyone, if you have more questions.
Okay.